Hey guys, welcome back. So today we're going to be talking about limits at infinity. We're going to be looking at limits as x goes to infinity. Before I get to that though, I would like to go over some of the homework problems. I know that this might have been a tough one. It depends upon how solid your algebra is. So I'm just going to run through a bunch of the exercises that were on the previous day's worksheet, and then we'll introduce some new stuff. So I'm going to go ahead and switch to my document camera, and I'm just going to do a handful of exercises, some easier ones and some hard ones. And yeah, we'll go from there. So maybe I'll just start with something that's a little bit straightforward, like say number 4. For 4, we're being asked to evaluate the limit as x goes to 0 of the function x squared plus 5x over x. Now, as we talked about last time, the very first thing that you always want to do is just try plugging this number into the function, right? You just want to plug that number to the function, because if you get just an ordinary number like 6 or 12 or something, then that's the value of the limit. So if you plug 0 in for x, we have 0 squared plus 5 times 0 all over 0. The numerator is 0. The denominator is also 0. And so we get that expression 0 over 0. Remember, that's a meaningless expression. That expression is not a number. It's not a defined expression. All it means is that you have to simplify your function somehow, rewrite it somehow, and then try plugging the number in again. Now, how can we simplify this expression? Well, you can factor the numerator in this case, because there's a common factor of x which can be removed. So I can pull out a common factor of x from these two terms here. Pulling x out of the first term leaves me with an x plus, and then pulling x out of the second term leaves me with a 5. And the reason that that's good is that now we see that there's actually a common factor of x that can be canceled from the top and the bottom. This one right here can be canceled with this one right here. So those two can be canceled, and we're left with simply x plus 5. So that is in fact the simplified version of our function. And now that we've simplified our function, we try plugging 0 in again. This time we get 0 plus 5, which of course is just 5. That is a perfectly ordinary number, and so that's the value of the limit. Okay. Number 5, very similar. We're asking you to evaluate the limit as x approaches 1 of x squared minus x minus 12 all over 5x minus 20. There are some things that can be factored here, but I think that what's surprising is that if you plug in the number 1 into this expression, you actually get an ordinary number to begin with. I think that what a lot of people do is they get into the habit of just like automatically factoring everything. If you factor the top and bottom of this expression, you get, let's see, I need a pair of numbers that multiply to -12 and add up to -1. I think that's x minus 4 times x plus 3. And then the denominator can be factored. There's a common factor of 5 that we can remove here. So that's going to be 5 times x minus 4. And then actually the x minus 4s do cancel. There is some cancellation here. And you're left with x plus 3 over 5. And you can plug 1 into this expression, and you'll get 1 plus 3 over 5, which is 4/5, and that's a perfectly ordinary number, so that's the value of the limit. Surprisingly, though, with this problem, you actually don't even have to factor anything. You can actually plug 1 into the original expression, top and bottom, and you'll eventually get 4/5, maybe after like reducing the fraction or something. You actually don't need to rewrite this function in order to evaluate the limit. But of course, as you're seeing in most of the problems, you typically do. Let's look at number 6. So that's a couple of examples where the simplification process involves factoring. Let's have a look at number 6, which requires kind of the opposite of factoring, namely you have to multiply out. So we're looking to evaluate the limit as x approaches 0 of quantity 4 plus x squared minus 16 all over x. So if you plug 0 into this expression, which you should do, you get, let's see, we get 4 plus 0 squared minus 16 all over 0. The denominator is certainly 0. And if you simplify it, so is the numerator, right? Because it's 4 squared, which is 16 minus 16. So that gives you 0 over 0. So we really do have to simplify this somehow before plugging in the number. So what can we do? Well, this expression here, 4 plus x being squared, you should multiply that out, right? This is one of the things that I talked about, right? If you see something that can be multiplied out like this, then you should do so. So let's go ahead and do that. So 4 plus x quantity squared, remember, a lot of people are tempted to say, oh, 4 plus x squared, that means just, distribute the 2 to the 4 and the x, but that's actually not allowed. In general, it's not true that a plus b squared, that is not equal to a squared plus b squared. Exponents do not distribute over addition in that way. So that's really not allowed. So when I say multiply out, what I'm really saying is this. I'm saying 4 plus x quantity squared, that really means, when you square something, it means you multiply it against a copy of itself, right? So 4 plus x quantity squared is really like 4 plus x times a copy of itself. It's 4 plus x times 4 plus x. And then we still have the minus 16 and then all over x. And so when I say multiply this expression out, I'm really talking about multiplying this expression out here. That's 4 times 4 plus, right? So let's go ahead and do it. So that's going to be 4 times 4 is 16, plus 4 times x is 4x, plus x times 4 is also 4x, and then x times x is x squared, and then minus 16 all over x. So we've multiplied everything out, but what you'll notice now is that there are actually some like terms to be combined. The positive 16 here actually cancels with that negative 16, so that's pretty good. So those go away, right? 16 minus 16 is 0. The two x terms can be combined, right? 4x plus 4x. That's going to give us 8x. So we have 8x on top. And then we have plus x squared still. Okay, so we've multiplied out, we've collected like terms. Unfortunately, you might think that you're done here. You might think, oh, plug 0 into this thing and I'm going to get the answer. But if you look, if you plug 0 into this thing, you still get 0 over 0, which means that there's still more work to be done. There's still more simplification that you can do. So what can you do? You might notice this problem here looks an awful lot like number 4. Remember we did number 4 a second ago, x squared plus 5x over x. And remember the trick here was to pull out the common factor of x in the numerator. The same thing is happening here. We've got a common factor of x in the numerator here that you can pull out. So if you do that, you're going to get x times quantity 8 plus x all over x. And now, finally, we see that we can cancel this x here with that one. So after canceling, we have 8 plus x. And of course, if you plug 0 into this expression, you do get, a perfectly ordinary, nice number. You get 8. So that's the value of the limit. Okay, so that's kind of a tricky one. The truth is, though, you shouldn't be too overwhelmed by this because the reality is there just aren't that many different kinds of problems. It seems like a lot at first, but after you've done enough of them, you'll see that there are really just 4 or 5 different types of these kinds of problems. Number 7, for example, is exactly like this problem. It's exactly like it. The numbers are different, but the structure is exactly the same. So don't feel too overwhelmed. Number 8 is an example of a limit problem involving square roots. And I sort of mentioned that this is something that you'll see certainly in AP Calc, but I don't think that you'll see it. I could be wrong. I don't think that you'll see it in foundations. So I told you to skip these if you're doing foundations. although certainly you can do it if you want to challenge. So number 8 is one of these expressions, involving a square root term. It's the limit as x approaches 3, square root of x minus square root of 3 all over x minus 3. As always, the first thing you should do is plug the number in, but I'll save us some time. If you plug the number in, you get 0 over 0. Okay, you can maybe see that in your head. You're going to get 0 over 0. So let's jump right to the simplification. So how do you simplify this thing? I said that anytime that you are trying to evaluate a limit that involves square root terms, you probably need to multiply top and bottom of the fraction by what's called the conjugate of the square root expression. Okay, the square root expression in this case is root x minus root 3, which means that the conjugate would be root x plus root 3. So we're going to multiply top and bottom by that expression. So I'm going to multiply the entire numerator by root x plus root 3, and also the denominator by root x plus root 3. You might be wondering, like, what justifies this operation? I mean, remember that when it comes to fractions, you can multiply top and bottom by whatever you want, as long as it's the same number, and you get an equivalent fraction, right? Like you can multiply top and bottom of a fraction by 2, and the same logic is true here. You can multiply top and bottom by even an algebraic expression, like involving a variable. As long as you're multiplying top and bottom by the same thing, it's actually going to be an equivalent fraction. So, okay, so what do we do from here? Well, you have to multiply some things out. You might remember in the video from yesterday, I said that you should only actually multiply out the expression involving, the root expression and its conjugate. That would be the numerator here. So you should multiply out this numerator here, but you should leave the denominator in factored form, because some cancellation is going to happen later. And if you multiply out the denominator, then it's much harder to see that cancellation is occurring. So I'll leave the denominator alone. I'll just copy it, x minus 3 times root x plus root 3. And then in the numerator, let's see. So root x, the numerator I'm actually going to multiply out. So root x times root x is just x, right? Root x times root 3, I suppose, is, well, there's a few different ways of writing it. I guess you could write it as just root x times root 3. Or you could write root 3 times root x, or you could put both the x and the 3 underneath the square root. It doesn't actually matter because this term is going to disappear anyway, because the next term, which is going to be this guy times that guy, is negative root 3 times root x. So that's just going to be minus the same term, minus root x times root 3, right? So these two terms are going to cancel, and that's always what happens in these conjugate problems. And then finally, the last term is negative root 3 times positive root 3, which gives you negative 3, okay? So as always, when you do these problems, these middle two terms cancel, right? So let's just get rid of them. The numerator then is just x minus 3, and the denominator, which I haven't really changed, is x minus 3 times root x plus root 3. And then now that we've done all of this, we can see that there's some simplification. There's some cancellation that can be done, right? This factor of x minus 3 will cancel with this factor of x minus 3. There's nothing left in the numerator, so that just means we write a 1. And then in the bottom, we just have a root x plus root 3. And now we've simplified our expression. So if you plug 3 into this expression, you get something reasonable. You get something that is actually a number. You get 1 over root 3 plus root 3. If I'm not mistaken, I think when kids do this problem, they get this far, but then they look at the answer and it's like not the same as what we have in the answer. That's because this expression can actually be simplified by quite a lot. So first of all, root 3 plus root 3, that's just 2 copies of root 3. So that's like 2 root 3. And then beyond that, this expression, you can actually rationalize the denominator, right? Like getting rid of the square root in the denominator. That's considered like bad form. I don't really have a great answer as to why people don't like square roots in denominators, like they're fascists or something, and they're very particular about these things, but it's a convention, so we should observe it. So just multiply top and bottom by, whatever the square root is. So multiply top and bottom of this expression, of this fraction by root 3. So if you multiply the top by root 3, 1 times root 3 is just root 3. And then if you multiply the bottom by root 3, it's 2 times root 3 times root 3. The roots will cancel. That's just 2 times 3, which is 6. So root 3 over 6, which is probably what you would see in a final answer. Yeah, so that's how that one goes. What else do we have? The complex fraction ones, like number 3 in the part 2 exercises, those are pretty hard. Let's go ahead and do that one. Yeah, we'll go from there. So number 3, this is number 3 from the part 2 exercises. It's the limit as x approaches 0, and you've got a complex fraction, which just means you've got fractions within fractions. So 1 over 2 plus x minus 1 over 2 all over x. If you plug in 0, I'll skip to the chase. If you plug in 0, you just get 0 over 0 eventually. So this does have to be simplified. How do you simplify it? The procedure for simplifying complex fractions is the following. You need to begin by making the entire numerator, like this entire thing, into a single fraction, and you need to make the entire denominator into a single fraction. Making the denominator into a single fraction is pretty easy. All you need to do is, instead of writing x, just write x over 1. There we go. Now it's a fraction. But as far as changing this whole numerator into a single fraction, you've got to combine these two fractions together, like it's one fraction minus another, and you've got to combine them together to get a single fraction. And in order to do that, you need common denominators, right? So you need common denominators, and a surefire way of getting common denominators is to multiply top and bottom of this fraction by this denominator, and multiply top and bottom of this fraction by that denominator. So let's go ahead and do that. So I'll multiply top and bottom. So first of all, here's my big fraction bar, right? And so I'm going to multiply top and bottom of this fraction by 2. That gives me 2 over 2 times 2 plus x. I'm not going to distribute the 2. Factored form is generally better, like for these kinds of problems. So I'm just going to leave it in factored form. And then minus, and I'm going to multiply top and bottom of this fraction by this denominator. So top and bottom by 2 plus x. So 2 plus x over 2 times 2 plus x. And just like that, I've got common denominators. This x over 1 doesn't really need to be changed at all. It's already a single fraction. So, okay, so now we're prepared to actually, combine these two fractions together. So let's go ahead and do that. Actually, there's a mistake that people tend to make on this problem that you really have to be careful of. I'll point it out. So it's this fraction take away this one. When you're adding or subtracting fractions, I think you probably know that you keep the denominator the same, right? Like you don't change the denominator. But what you have to do is combine the numerators. Like it's going to be this numerator minus this numerator. The mistake that people tend to make with this problem is pretty common. When you're subtracting a fraction, as we are here, like we're subtracting this whole thing right here, this minus sign needs to get applied to the entire numerator of this fraction. Like you're subtracting all of the numerator here. In other words, you're subtracting both of the terms in the numerator. So you're subtracting both the 2 and the x. And people tend to forget that, and they tend to just write like, they'll write 2, because of this 2, and then minus 2, and then they'll typically just write plus x, but that's wrong. The minus sign needs to be applied to both of those terms. So it's actually 2 minus 2 minus x. So if you were getting almost the right answer for this problem, but you were getting like the opposite of what it should have been, probably this is what happened. Anyway, So there's a little bit of simplification. Obviously, the 2 minus 2, that can just be canceled. So it's just, so here's my big fraction bar. In the numerator, I've just got negative x over 2 times 2 plus x. And then on the bottom, I've just got that x over 1. So, all right, so now we've finally combined the entire numerator into a single fraction, right? So this is kind of where you want to be. To simplify a complex fraction, you need to make it so that the entire numerator is a single fraction, and I've done that, right? The whole top is just one fraction, and the whole bottom is just one fraction as well. So I've successfully done that. Once you've gotten a single fraction up top and a single fraction down below, what you have to do is use what is sometimes, there's a cute phrase for this. It's called keep it, change it, flip it. Really what's happening is you're taking one fraction, like this guy here, and you're dividing by another fraction. Well, dividing by a fraction is the same thing as multiplying by its reciprocal, right? By like its flip. So this is really the same thing as that top fraction, negative x over 2 times 2 plus x, times the reciprocal of the bottom fractions. That's 1 over x. But another way of saying that is keep it, change it, flip it, because what I've done is, I keep the top fraction, right? So I keep the top fraction, no change. I change the division sign to multiplication, and I flip the bottom. So keep it, change it, flip it, right? So you keep the top fraction, change the division to multiplication, and flip the bottom. Keep it, change it, flip it. It's kind of cute. Well, at this point, there is one nice thing that can be done. This x right here will cancel with that x right there. It's a common factor on top and bottom. So those will go away. Do be careful. That minus sign is still there, though. That minus sign is not going away. So what do we have in the numerator? Well, the minus times the 1 gives you negative 1. And then in the denominator, I've got 2 times 2 plus x. Finally, this is your simplified expression. And now we finally just plug 0 into this expression, and we actually do get something reasonable, right? We get negative 1 over 2 times 2 plus 0, which is negative 1/4, and that's the value of the limit. As you can see, a lot of these problems are really just like exercises in algebra is really all it is. Like number 5 from the same section is pretty fast, but you have to remember what to do. It's the limit as x approaches 2, x squared minus 4 over x minus 2. This guy can be factored. The numerator can be factored. It's a difference of 2 squares, like x squared minus, and then 4 is also a square. It's the square of 2. So you can rewrite that as, x plus 2 times x minus 2, right? So that's how a difference of 2 squares factors. And then this x minus 2 cancels with that x minus 2. So the whole thing just reduces to x plus 2. And now when you plug 2 into this expression, you just get 4. So that's how that one goes. I know there's some tougher ones on here, like number 9 from the same section tends to be pretty tricky. If you couldn't get through that one, I wouldn't worry too much about it. It's kind of you'll have more time to practice it next year. But I've already spent long enough going over the problems on here. So, okay, yeah. So I think that's good for homework review. Yeah, don't forget that, if you're doing these problems and you're just like, yeah, I'm not getting any of them, like I really don't understand how to do it, like just email me, right? And I'll explain any of these that you want, or like meet with you individually, whatever you want to do. Always happy to talk about math. So, okay, so I'm going to switch back to my computer screen here, and what we're going to be talking about today are infinite limits. That's the new topic. So actually I think I'll actually work from my notebook still. So so just some notes. So infinite limits. So what is an infinite limit? What does it mean? So here's the idea. The limit as x approaches infinity of some function. What does this expression mean? It means the value that the function f approaches as x gets really, really big, like really, really, really big, like bigger than 100, bigger than 1,000,000, bigger than 1,000,000,000, bigger and bigger and bigger. Like lots of other limits, this thing is not guaranteed to exist. As x gets bigger and big, in fact, most of the time this thing doesn't exist. Like if you take most functions, if you let x get bigger and bigger and bigger, the function typically does not converge or settle down to any particular value. And so usually this thing is not a number. Usually this thing doesn't exist. But I should also mention that we sometimes look at the limit as x goes to negative infinity. As you can probably imagine, that's the same thing, except you're asking essentially what happens as x becomes a really, really, really big negative number, like negative 100, negative 1,000,000, negative 1,000,000,000. So it's pretty much the same thing, just as x becomes a really big negative number. So just to kind of show you like what I mean by this, and just to give you a sense, let's consider the following. Let's let f of x be the function 2 plus 1 over x. Okay, so this is just some function, and I would like to compute the limit as x goes to infinity. Right? I'd like to know what value does this function approach as x becomes really, really, really big. We're going to learn a fast way of doing this today, but since this is the very first example, and I want to make sure you understand like conceptually what this limit is about, we're going to do it in a little bit more of a numerical way. So let's just imagine plugging in larger and larger and larger values for x, right? Because what this limit is all about is it's about like what happens as the input x gets bigger and bigger. So let's plug in some large numbers and see what happens. If you plug in 100 into this function, f of 100 is 2 plus 1 over 100. If you convert 1 over 100 to a decimal and add it to the 2, that's 2 and 1/100th, which as a decimal is 2.01. Okay. What if we plug in an even larger number, like 1,000? Well, that would be 2 plus 1 over 1,000, which if you convert that to a decimal is 2.001. Probably you can already see where this is going, but just in case, let's go even further and plug in an even larger number. How about 10,000? Okay, if you plug 10,000 into this function, you have 2 plus 1 over 10,000. As a decimal, that's 2.0001. Okay, so what can we conclude? I mean, as x gets larger and larger and larger, what's happening to the value of the function? It's getting closer and closer and closer to 2, isn't it? So we can conclude, just by looking at these numbers, that the limit as x approaches infinity of this function is 2. Because as x gets bigger and bigger, this function's value gets closer and closer to 2. Okay, so that's what we mean by infinite limits. Just very clearly, like most functions don't have an infinite limit. Like suppose that we did the same thing. I'm not going to do it all the way out, but suppose we did the same process, except suppose that our function were like x squared. Imagine plugging in larger and larger values to that function, right? If you plug in 100 into this function, you get like 10,000. I want to say, right? If you plug 1,000 into this thing, then I think you get 1,000,000. If you plug 10,000 into this thing, then you get, I don't know, I don't know how many zeros. But if you plug larger and larger numbers into this function, the values will not be approaching a number. Rather, the values of the function themselves are just going to get larger and larger and larger, right? The outputs are not going to be settling down or converging or approaching any number like they were here. They're just going to get bigger and bigger and bigger. So the limit as x goes to infinity of this function is a little less interesting. It's not a number. We would just say, I mean, technically it doesn't exist, but we would say in parentheses infinity. And what we're saying there is that it's not converging, right? Like the output values are not converging to any particular number. So the limit doesn't exist. And specifically, it's failing to exist because the output values are just getting bigger and bigger and bigger. So that's actually kind of typical. Like most functions don't have an infinite limit if you pick a random function in the wild. However, most of the functions that you'll see on today's worksheet do have an infinite limit. Because when they don't have an infinite limit, there's kind of less to say. It's sort of more interesting when they do. So most of the problems you'll see on today's worksheet will have an infinite limit, like this first example, but just understand that it's perfectly common and ordinary for functions to not have an infinite limit. Okay, so how do we, so the question now is really, how do we evaluate infinite limits without actually plugging in numbers all day? Because as you can imagine, this is kind of tedious, right? This gets kind of tedious plugging in numbers over and over again, especially if your function's more complicated, right? This is a pretty simple function. It's like just 2 terms, pretty easy to plug numbers in. But if we had a more complicated function, you can imagine it would take a long time to plug in larger and larger numbers and sort of ask what happens. So we're going to introduce a way of evaluating these infinite limits quickly. So the key to evaluating infinite limits is what I call the hierarchy of growth. Hierarchy of growth. Hierarchy is kind of a fancy word, but it just means like an ordering essentially. Yeah, so the hierarchy of growth is really just a description of how quickly different kinds of functions grow. Okay, so it's really about how quickly different functions grow. That's what it's about. Yeah, so really there's lots of different kinds of functions in the world, but I'm going to try and summarize here just a description of like which functions grow the most slowly and which ones grow the most quickly. And that's all going to be explained in basically this chart. So way over here on the left end, which is to say like the slowest growing functions, we've got constant functions. Okay, remember like a constant function is a function that doesn't grow at all, right? Like the function f of x equals 3. That's a constant function. That function is always equal to 3. It doesn't grow at all. As x gets bigger and bigger, the output is staying exactly the same. The output is always 3, no matter what the input is. So constant functions don't grow at all. So these guys are among the slowest growing functions out there. They don't really grow at all. But I would also put some other functions here, namely the sine function and the cosine function. Now, those functions are not constant. So you might be wondering why I say that those guys grow the most slowly. They're not constant. But if you remember what they look like, the sine and cosine functions, they kind of look like this, the graph. They just, bounce up and down. The fancy word is they oscillate, like they just go up and down over and over again. And so as x is getting larger and larger, in other words, as you go further and further to the right in the graph, the function's value is not getting larger and larger, right? As a matter of fact, these functions always stay between +1 and -1, like they never really exceed those values. They just kind of bounce between +1 and -1. So as x gets bigger and bigger, these functions don't actually grow. They just kind of bounce a little bit. So that's why I place sine and cosine along with the constant functions in the slowest growing category. Okay, so this is the slowest growing category of functions, constant functions and also sine and cosine. After that, I'm going to make a big less than sign. So this is a giant less than sign. After that, we have the next group of functions, which are powers of x. Okay, so powers of x, like for example, x squared, x to the third, x to the fourth, all that kind of thing. So I'm going to write some symbols here and I'll explain what they mean. I'm going to write x to the 1/2 is less than x is less than x squared is less than x to the third. And then I'm going to write ... to just indicate that this pattern continues, this sequence continues. So powers of x, when I say powers of x, I mean functions like this, right? X squared is a function, x to the third is a function, x to the 1/2 is a function. Those are all functions that you could describe as powers of x. And what do I mean with these less than signs? I mean a couple of things. First of all, x to the third grows faster than x squared. That's why I'm saying x squared is like less than x to the third. I'm saying x squared grows less quickly than x to the third. And x squared grows more quickly than x. And x grows more quickly than x to the 1/2. Okay, so basically within this family, the larger the exponent, the more quickly the function grows. Not surprising. By the way, this family of functions actually includes roots. It includes like square root of x and third root of x and all of that stuff, because remember that root functions are just powers of x, right? So remember that like x to the 1/2, that's just the square root of x. X to the 1/3, that's just the third root of x. So this family of functions actually includes root functions, okay? So, you know, yeah, and by this big less than sign here, what I'm telling you is that every function in this category grows more quickly than every function in this category. Okay, that's what I'm saying with this big arrow here, this big greater than, okay? So I've got two families of functions. And then I'm going to have another big, you know, arrow like this, because I want another family of functions. And these are the exponential functions. Okay, the exponential functions look like this, like 2 to the x is less than, I'm going to write e to the x. E is a special number. You saw it if you took pre-calc honors. It's just, it's like 2 point something. If you haven't seen e to the x before, just ignore it. It's okay. Just understand that e is just a special number. It's like 2.6. But anyway, that's less than 3 to the x, which is less than 4 to the x, and so on, right? So exponential functions are functions where the variable is in the exponent, right? As opposed to these guys here. Notice the difference, like powers of x versus exponential functions. Exponential functions, the variable is in the exponent. So what am I saying here? I'm saying that within this family, the larger this number here, which we call the base, the larger this number here, the more quickly that function grows. So 4 to the x grows more quickly than 3 to the x, which grows more quickly than e to the x, because e is like 2 point something, which grows more quickly than 2 to the x, and so on. And what I'm saying with this big arrow here, with this big greater than sign here, is that every function here grows more quickly than every function here. So you can take, so which is kind of surprising. Like if you take a slow function from this category, like 2 to the x, take 2 to the x, right? And then take a really fast function from this category, like x to the 100. So x to the 100 versus 2 to the x. So this function is from this category. It's a very fast growing member of this category. And 2 to the x is from this category. It's a very slow growing function from this category. Nevertheless, I claim that 2 to the x actually grows faster than x to the 100, eventually. If you compare, the graphs of these two functions, for a very long time, this function is actually going to be larger. But eventually this function will catch up. For it'll take a long time, like maybe it catches up at x to the 1,000 or x to the 10,000, I don't know where. But eventually this function will catch up and outpace this one. So when I talk about growth and the rate of growth, I'm really talking about the growth rate as x goes to infinity, as x gets bigger and bigger and bigger. Okay, so, all right, so that's the hierarchy of growth. It tells you, how quickly different functions grow. And as I said, this is really the key to evaluating infinite limits quickly. So let's take a function that looks really complicated, okay, and try to evaluate the infinite limit. So let's take the limit as x goes to infinity of the function 5x to the 4th minus 2,000 x to the 3rd plus 7 over 6x to the 4th minus cosine of x plus 1. Now, if you can imagine, remember we were plugging in numbers, like large numbers, to evaluate this infinite limit. Imagine how long that would take with a complicated function like that. Fortunately, all we need to evaluate this infinite limit is this hierarchy of growth. So here's what you do. You look at the numerator and you identify the fastest growing term in the numerator. So pretty clearly, so this is a constant term, that's a constant function, that's in the slowest growing category, right? X to the 3rd, okay, that's in this category. And x to the 4th, that's also in this category, but the x to the 4th term wins out, right? Because the exponent is higher. So this is actually the fastest growing term in the numerator. You might look at the coefficients, you might be like, oh geez, like that 2,000, isn't that like a really big number? Like, wouldn't that make the 2,000, wouldn't that make this middle term actually grow more quickly than this term? The answer is surprisingly no. At first, for small values of x, this term will be bigger, will grow more quickly than this one. But eventually the x to the 4th one will catch up and outpace it. So this is the term that grows most quickly in the numerator. In the denominator, it's also the x to the 4th term, right? The cosine function, that belongs in the slowest category, and the 1, that's also a slow growing function. So you identify the terms which grow most quickly in the top and the bottom. Why do you do that? Here's why. As x goes to infinity, as x becomes really, really big, these two terms, because they grow so much faster than the other terms, that for very large values of x, they'll actually be so much bigger than the other terms that you can just ignore the other terms. In other words, for really big values of x, this term is so much larger than the other two in the numerator that you can just ignore the other two terms. It's, this will be like 800 billion, and by comparison, this will be like, some much smaller number. So the idea is you just ignore the slower growing terms. You only keep the fastest growing terms. And what that does is it allows you to work with a much simpler function, right? Technically, this function is not the same as this one, but I claim that their infinite limits are the same. So what's going on here? Well, you'll notice now that I can actually cancel the x's, right? I've got x to the fourth over x to the fourth. So you can cancel those x's entirely, and you're just left with 5, 6, and that's the value of the limit. It's very fast, right? So if you plug in a giant number into this function, like if you plug in 1,000,000 into this function, you'll get something very, very close to 5, 6. And the bigger number that you plug into this thing, the closer the output will be to 5, 6. Okay. Let's do another one. Let's do something like the limit as x goes to infinity of 3x squared minus 2 over e to the x plus 4 x to the 6th. Okay, so again, what do? We need to identify which terms grow the most quickly in the numerator and the denominator. In the numerator, that's definitely the 3x squared, right? And that grows faster than the 2, which doesn't really grow at all. And the bottom, it's the e to the x, right? Because that's an exponential function which grows faster than any of these guys, right? It grows faster than the x to the 6th, certainly. So we ignore the slower going terms, and we have a simpler function to work with, 3x squared over e to the x. Unlike the previous example, nothing really cancels. Like this x here doesn't cancel with these x's up here or anything like that. But there is some analysis that we can do, because as x is going to infinity, let me ask you, does the numerator grow faster or does the denominator grow faster? It's the bottom, right? The bottom grows faster. It's an exponential function, whereas the top is just a power of x. So the bottom grows much more quickly. So that means that as x gets bigger and bigger, the bottom of the fraction is going to be much, much larger than the top of the fraction. So you have a fraction where the bottom is getting really, really big, and in comparison, the top is a lot smaller. So if you have a fraction where the bottom is much, much bigger than the top, then the overall value of that fraction is very, very small. It's like 10 over 100, or maybe 100 over a billion, right? If the numerator is much, much smaller than the denominator, then the overall value of that fraction is very small, which means that as x gets bigger and bigger, this fraction's value is getting smaller and smaller. In other words, it's getting closer and closer to 0. Okay, so it's approaching 0. And sure enough, if you plug a huge number into this expression, you'll get something very close to 0. Okay, let's do one more. Let's try the limit as x goes to infinity of 3x minus 4x to the 5th over 7 cosine of x plus 2x to the 100. Or no, not 2x to the 100. I meant, let's, I want to change this, my bad. Let me make this 3x, so 3x to the 4th. And I want to make this bottom term 100x. There we go. Sorry about that. Okay, so that's the function I want to look at. So what do? Identify the fastest growing terms. So in the top, that would be actually this guy, right? That'd be this guy right here. That's negative 4x to the 5th. On the bottom, the fastest growing term is this guy right here, right? Because that's a part of this category, whereas the cosine function is in the slowest growing family, so over 100x. There is a little bit of cancellation that can be done. You can cancel this x here with one of the copies of x on top. So that's negative 4x to the 4th over 100. And now what happens as we let x go to infinity? in this expression. As x gets bigger and bigger and bigger, think about what happens to the fraction. The denominator is staying the same. It doesn't even have an x in it, right? The denominator is just 100, it's constant. So as x is getting bigger and bigger, the bottom is just staying fixed at 100. But as x is getting bigger and bigger, the numerator is becoming a larger and larger negative number, right? Because it's being multiplied by -4. So for very large values of x, the numerator is going to be like -1,000,000, and the bottom is going to be 100. So as you imagine x getting bigger and bigger and bigger, the sequence is going to be like -1,000,000 over 100, -1,000,000,000 over 100, -1,000,000,000,000 over 100. But what's happening to those values, right? What's happening to the value of the fraction as x gets bigger and bigger and bigger? It's not converging to a number. In fact, the overall value of the fraction is becoming a larger and larger negative number, right? Like -1,000,000 over 100, -1,000,000,000 over 100. That's just becoming a larger and larger negative number. So this expression, as x gets bigger and bigger, is actually going to -infinity. It's becoming a larger and larger negative number. If you're having trouble seeing that, plug in some specific numbers. Like actually try plugging in 10, and then plug in 100, and then plug in 1,000. And you'll see very quickly you're getting larger and larger negative numbers, which makes sense because the numerator is becoming a larger and larger negative number, but the denominator is staying fixed at 100. So if you have a fraction where the top is getting much, much bigger than the bottom, the overall value of the fraction is getting larger, but of course these numbers are negative, so it's going to -infinity. Okay, so that's it for today. Like always, try to check your answers with the exercises that we give you. And as usual, there's a range of difficulty in these problems. Remember that this class is meant to be accommodating for like several different levels of students. So like if you're like really not sure about some of the problems, that's okay, that's fine. But if you, but certainly if you're going into AB, then you should be able to do the majority of them. If you're having trouble, make sure you just email me and get some help. Okay, I will see you guys next time.